welcome back on board the Starship, and we're talking with John Duffield, and we're talking about physics. Now, quite often people think they understand things, John, but actually perhaps they don't. So what would you say is a good test?
There's an old saying that's down to Einstein. You do not really understand something unless you can explain it to your grandmother.
Okay.
If you think you understand something, if you can't put it into simple terms, then maybe there's an issue.
Okay.
And one of the issues is that mathematics actually deals with the relationships between terms. If you look at a simple expression like E equals mc squared, the mathematics doesn't actually tell you what E is. It doesn't tell you what the M is or the C. Unless you've got an idea of what these things really are at a fundamental level, then you run the risk of going around in circles.
Well, E is energy, M is mass, and C is the speed of light.
Yes, there's another C, a big C, which is charge.
Okay. And so mathematics is the usual tool that physicists use to try and unravel the understanding of physics, isn't it?
Yeah, it's a vital tool, it's a fine tool, but sometimes it's just not enough. Sometimes you need other tools, like simulation and analogy, basically anything you can lay your hands on.
Right, okay.
Then you can crack it.
Just to go back to the electromagnetic wave, you know, there are tools or diagrams we can use to explain electromagnetism, aren't there?
Yeah.
It's quite a difficult, because if space is, or the nature of space, if it's got waves going through it, radio waves, you can't see it. So how do you start to understand something that's completely invisible to you?
Well, you can understand waves in terms of surface waves on the ocean. They undulate like this. But then the tricky bit is to try and imagine a wave inside a bulk. This is not a surface wave. So you think it's got to be something like a pulse or a throb.
Right.
So then you start thinking in terms of something that undulates, but is symmetrical here and here, and therefore you end up with something rather like a lemon, a curved, pointy lemon that shoots through space at the speed of light.
Right, it's like a pulse. And this is what an electromagnetic wave looks like. You said that, you know, you can think of ripples on a pond to describe an electromagnetic wave, but it's not quite like that, is it? Because you've got the magnitude of an electromagnetic wave is fixed. Is that?
When you look at any picture of the electromagnetic spectrum, what you see is the high frequency waves at one end and the low frequency waves at the other. Now, the actual height in the depiction is the same for all the waves.
Okay.
This is an electromagnetic amplitude, but underlying it there is something called Planck's constant.
Right.
This is the quantum of quantum mechanics. There's a little expression which is E equals hf. The h is Planck's constant of action. When you go back to the original electromagnetism done by Maxwell, he's talking about displacement. So you can then imagine that you've got a wave which is like a pulse where the displacement is the same regardless of frequency. So if you're thinking in terms of lemons, all the lemons are the same height. Some are very long, some are very short, but they're all the same height.
And if we look at a beam of light, you know, coming from the sun or an electric light bulb, there are actually trillions of individual photons in that beam, aren't there? So
trillions of individual pulses of light, and they're all 3.86 times 10 to the minus 13 meters in terms of the displacement or how much they pulse, how much they make the space move.
And the other thing that's, you know, we have analogy of ripples on a pond where photons are different is that they don't their energy never decreases as they fly through space. So even if they're coming from the other end of the universe, the energy in a photon is the same when it hits your eye. Am I right?
Yeah. There is something called the tired light theory. It's not one that I particularly like. But in terms of energy, have you ever been on a ship?
Yes.
have you ever been on a big ship on a calm ocean?
Yeah.
I have, and what I've noticed were the oceanic swell waves.
Mhm.
Now, these are great big things, perhaps 1,000 feet long,
Mhm.
and they glide across the ocean.
Mhm.
It's like a hump. It doesn't dissipate.
Mhm.
It's just a wave.
Mhm.
It just keeps going. It doesn't spread out.
Mhm.
Photons might work in a similar fashion. Some people I talk to say that it's because there's orbital angular momentum involved.
Right.
On an oceanic wave, actually, the water moves in a rotatory fashion.
Right.
You can see this on the internet.
Uh-huh.
But waves don't spread. A ripple will spread out, but
Yeah.
if you look at an oceanic swell wave,
Mhm.
it just goes along.
Okay. Yeah. So it doesn't lose. The energy doesn't dissipate.
No.
It's just, well, we think of the inverse square law. It's just the number of photons gets less the further you are away from a source. So therefore,
It's like a ripple in a rubber mat. If you shake the mat like this, the ripple, it propagates down the mat. It doesn't dissipate.
okay,
It's because that's the way the rubber mat is.
okay,
There's stress involved and there's tension involved. There's always got to be stress and tension together.
to create a wave.
Yeah.
Okay, now electromagnetic wave it's a little bit more complex than that, isn't it, John? Because there is a twist element to an EM wave. Am I right in that? And that it's got this circular motion as it's going forwards.
It may have.
Okay.
I think that's getting quite hard to visualize.
Uh-huh.
If you were to look at a lattice depicting space, if you follow the lattice along, the lattice lines they start off, say, horizontal. As you move along this lemon-shaped distortion, they turn, they tilt. Then at the top of the lemon, they go flat, and then they tilt the other way. You can see this tilting as the twist.
Yes.
It doesn't have to be another twist, though there might well be.
Okay.
We really need computer simulation
Yeah.
to check into that.
So if there's anybody watching out there who's a fantastic, computer animator who can animate some of these, twists and turns and waves, etc., it would be good to try and model what you believe to be the photon and how that then manifests itself as an electron or even as a proton.
Ideally, we'd like to simulate in a lattice model a photon. We'd also like to simulate an electron, and we'd also like to simulate pair production, where a photon is turned into an electron and a positron.
Okay, right. Okay, now so we've got our electron in space, which is essentially a photon in this knot. But how does it exhibit charge? Because particles have charge which attract or repel each other depending whether they're the same charge or not. So what's the visualization of charge?
There is something called the thalakosoliton. You dip a plate into some water, and you stroke it forward whilst lifting it clear, and you get a U-shaped double whirlpool. Now, you can play around with these solitons in a pond, and if you watch carefully, the left-hand side of one repels the left-hand side of another. Ditto for the right and the right, but the left and the rights attract.
Okay.
If you aim two at one another face on, you get an analogy of annihilation.
Right.
Bang, they're gone.
Right. So this is like whirlpools in a pond.
It's only a fluid analogy,
Right.
but you can get a real grasp of the sort of thing that's going on with an electron, which is akin to a whirlpool, but it's not fluid, it's not in a pond, it's stress going round in space.
Okay, and that whirlpool is effectively what an electric field is then?
Yes and no.
Okay.
The way it generally works is that you have got a stress going round in space, and that distorts the surrounding space. It pulls it around.
Okay.
So the electric field is, in essence, distorted space.
Right.
It's similar to something called frame dragging.
Right.
If you
And it's
imagine this,
three-dimensional as well.
Yeah.
We're in the whirlpool. It's very flat, isn't
It's-
it? But
it's
it's in every direction. This distortion.
if you imagine a lattice,
Uh-huh.
reach in, grab the lattice, turn it.
Uh-huh.
Now reach in from here, grab it again, and turn it again.
Right.
There's more than one rotation.
Right. Okay. And that twist drops off as per the inverse square law. The further away you get from it, the closer you get to the electron, the more space is twisted in those two directions.
Yeah,
Is that?
you can think in terms of what's called a Fibonacci spiral.
Yes.
This is where the amount of spiraling decreases with distance.
Now let's bring in a second electron then. We've got our electron, which has got twisted space in two directions, and we've got another electron which comes along. What happens?
Well, the electron does have a rotation to it, so it's rather like two whirlpools which are spinning in the same way. They drive each other apart.
Right. Okay.
Whereas two whirlpools going in the opposite direction, they pull each other in.
Which would be a positive and a negative charge. Okay.
However, that's in essence the electric field. Another field is the magnetic field, but there's only one field there. It's just the electromagnetic field. The magnetic field is where one whirlpool is sitting here and another one is moving past it. What happens is that you get rotational motion as well as linear motion. There's a rotational motion too. You can think of two whirlpools moving around each other. But the phallico-soliton and the whirlpools is, I think, the key to getting a handle on what's really going on.
So an electric current is when we have charged particles moving in a direction.
Yeah. Typically, electric current is the motion of charged particles. However, it's not necessarily that. If you think about a photon, it's an electromagnetic wave.
Right.
The field is varying.
Right.
It's varying like this. There is a form of current there. There's no charged particle.
Right.
But if the field is varying, there is some current.
Okay.
It's akin to what's called a displacement current.
Okay. I think I understand. So basically, this is the fundamental principle by which all motors and generators on Earth work. It's the interaction of one piece of charge which is moving against another, which then push each other apart, and hence your motor works, or generator.
You can demonstrate this via the right-hand rule. In the right-hand rule, the current's going this way, the magnetic field lines go this way. The electrons moving up here mean that an electron here will move in a circular fashion. If there was just electrons in the wire and they weren't moving, an electron here would move in a straight fashion.
Okay.
But simple relative motion converts linear motion into rotatory motion. It's rather like a drill bit. In fact, Maxwell talked about a screw mechanism in 1867. You can actually, again, get a feel for it with a reamer. If you hold a reamer in your hand, you can push it up with your thumb, and you can feel how the linear motion turns into rotatory motion.
Yes.
That's how all electric motors work. The current goes this way, the motor goes this way.
Yeah. Yeah. Okay.
Every electromagnetic phenomena you can think of works like this. It's all to do with twist and turn. The electric field is a twist field, and the magnetic field is how you see it when you move through it.
Yeah.
It's twisted space, therefore when you move through it, you turn.
Yeah.
It's
Just the
simple.
space itself is twisted.
Yeah.
Right. Okay. Okay then, John. Well, thank you. It's time now for our Artist of the Week, but we will talk more after the break.
Feels like a race. You're miles off the pace, and our eyes still lean for the line. sponge and that's welcoming the outside. Skin becomes a sponge, welcome all the outside in. Recognize the beach and all